Welcome to our channel Learning Math. In this video, we're going to learn about an introduction for limits of functions for grade 11, how to calculate the limits. First, sure, what are the limits, what are the indeterminate limits, and how to calculate limits in such cases with some applications on them. Before starting and for the continuity of our channel, please like, share, and subscribe with a great appreciation for your support. Now let's start together by some examples. If we have, for example, f of x equals 1 over x. Well, let's understand graphically first what's the meaning of a limit, then we're going to learn how to calculate limits. As you see here in the following graph, as x tends towards minus infinity, the graph of f of x approximately it approaches 0. We say in this case that limit for f of x as x tends to minus infinity will be 0. Well, on the other hand here, if you note something, if we think about x, it's approximately 0, but it's less than 0. We say here x tends to 0 minus. Well, what happened to f of x in this case? As you see, it tends towards minus infinity. So we can say that limit for f of x as x tends to 0 minus is minus infinity. Well, what happens here? For x tends to 0, here as you see x is approximately 0. If you note it, x is approximately 0, but x is still greater than 0 a little bit. Well, what happened to f of x? F of x tends towards plus infinity. So in this case, we say that limit for f of x as x tends to 0 plus, which means x tends to 0 and greater than 0 a little bit, the limit of f of x in this case is plus infinity. Well, if you know something, here x approaches plus infinity, while f of x is approximately 0. So we can say that limit for f of x as x tends to plus infinity is 0. Let's learn together how to calculate the limits. Actually, when we have the function f of x equals 1 over x, then its limit at plus or minus infinity will be 0. Let's have some examples to understand it more. If we have x, for example, is 100, then 1 over x will be 0.01. It's approximately 0. Now let's increase x a little. If we have x, for example, is 1000, then 1 over x will be 0.0001. Also here we have that 1 over x is approximately 0. So the more x increases and x tends to plus infinity, then f of x, which is 1 over x, will tend to 0. Here we say that limit for f of x at plus infinity is 0. Another example. If we have x tends to minus infinity, for example, let's have x approximately minus 100. Then 1 over x will be 1 over minus 100, it's minus 0.01. Also, it's approximately 0. Well, another example. If x is minus 10,000, then 1 over x will be minus 0.0001. It's also approximately 0. So as x tends towards plus or minus infinity, then f of x, which is 1 over x, will tend to 0. What happens if x tends to 0 minus? If we have, for example, x is minus 0.01. Here we say x tends to 0 minus. Why? It tends to 0 and it's still negative. It's less than 0 a little bit, minus 0.001. Then 1 over x will be minus 100. It will increase, but in the negative sense, so it tends to minus infinity. Another example, if we have x is minus 0.0001, we have 1 over x will be minus 1000. So as x tends to 0 minus, we will have 1 over x, it will tend to minus infinity. We say in this case limit as x tends to 0 minus for f of x, which is 1 over x, will be minus infinity. What happens if x tends to 0 plus? What does it mean 0 plus? X tends to 0 and x is greater than 0 a little bit. For example, if we have x is 0.1, it's approximately 0. We will have 1 over x, it will be 10. If x is 0.001, then 1 over x will be 1000. So as x tends to 0 plus, then 1 over x will tend to plus infinity. It will increase. Here we say that the limit of f of x, which is 1 over x, as x tends to 0 plus, is plus infinity. Another example. If we have here, for example, here f of x equals x squared minus 9 over x minus 3. Well, if we think about it as x tends to 3, first of all, we should say that x is different from 3 since we can never divide by 0. If x is 3, then on the denominator we will have 3 minus 3 is 0. If we think about it logically, we cannot divide by 0. But if you know something, also for 0, x squared is 3 squared, which is 9. 9 minus 9 over 3 minus 3 is 0 over 0 indeterminate. We cannot calculate 0 divided by 0. Well, what should be the limit of f of x in this case at the value x equal 3? Well, if you know something, we can write x squared minus 9 as x minus 3 into x plus 3. Well, now we can simplify x minus 3 by x minus 3. Now what should be the limit of f of x as x tends to 3? Here we can replace x by 3. Then the limit for f of x is 3 plus 3. It will be equal to 6. Note that since this limit exists, we can say that f of x will be continuous at x equals 3, and note that f of x is 6. Another examples. Well, if we have, for example, f of x equals radical x. Sure, since below the radical, x is below the radical, the function is defined whenever x is positive. So, as you see here, the domain, as it's in the figure represented, is from 0 towards plus infinity, from x equals 0 to plus infinity. Well, note that as x tends to plus infinity, f of x here tends to plus infinity. So, as you see, the limit of radical x at plus infinity, we say it's plus infinity. Another example, if we have, for example, f of x equals x squared, let's study it graphically, then we're going to learn how to calculate the limit. Note that here, as x increases, we say x tends to plus infinity. What's happening to the function f of x? As you note, it tends towards plus infinity. Also, as x decreases, which means x tends to minus infinity, f of x will tend to plus infinity. Why? Since minus infinity squared will be plus infinity, minus over the even power will become plus. So we can say in this case that limit of f of x as x tends to minus infinity, which is limit for x squared as x tends to minus infinity, it's plus infinity. Also, the limit of this function at plus infinity will be plus infinity. Now let's take another example. If we have the polynomial or the function f of x, which is a fraction of two polynomials, it's 5x squared plus 6x plus 9 over 3x squared plus 2x minus 3. Well, if we think about limit for f of x as x tends to plus infinity, how to calculate this limit? Note that x tends to plus infinity, then we can say that x squared tends to plus infinity, and 6x will tend to plus infinity. So the sum here will tend to plus infinity. What about the denominator? X tends to plus infinity, then x squared or 3x squared will tend to plus infinity. The same here, plus 2x will also tend to plus infinity. Minus 3 will not affect, then the denominator will also tend to plus infinity. In this case, we will have the limit of this function is plus infinity over plus infinity, but this is an indeterminate form. We cannot calculate its answer. Well, you may ask, can't we calculate the limit in this case? Actually, we can. How to calculate the limit of f of x in such cases? We take on the numerator the highest degree of x, which is here x squared with its coefficient. And on the denominator also we take the highest degree of x, which is here x squared with its coefficient. Then the limit of f of x at plus infinity will be equal to the limit at plus infinity for 5x squared over 3x squared. To understand it more, let's solve it together. Can't we say that the limit at plus infinity For the numerator, which is 5x squared plus 6x plus 9, can't we write it as x squared into 5x squared plus 6x plus 9 all over x squared? Note that here we can simplify x squared by x squared. It returns back the same. Well, on the denominator, the same. We can multiply and divide by x squared. Well, why did we solve it in this case? To understand it more. Note that we can distribute it here. We can write it as 5x squared over x squared, as you see, plus 6x over x squared plus 9 over x squared. Now we're going to simplify and solve together. Also on the denominator the same. We copy x squared here the same. Now we can distribute the fraction. We can write it as a 3x squared over x squared, as you see here, plus 2x over x squared, we write it, minus 3 over x squared. Now why did we write it in this case? So here we have distributed the fractions all over the numerator and the denominator alone. We have written it in this case so that we can first of all simplify x squared by x squared. It will not affect the limit anymore. Also here on each fraction we're going to simplify x as much as is possible. So here as you see on the first one we can simplify x squared by x squared, we get 5. On the second fraction we can simplify x by x squared, we get it 6 over x. Sure, plus we copy the sign. Here plus 9 over x squared also we cannot simplify it, we write it the same. What about the denominator? 3x squared over x squared, here we can simplify x squared by x squared, we get 3. Now plus we copy it. 2x over x squared, we can simplify x with x squared, we get it 2 over x, as you see. Now minus, sure we copy it. 3 over x squared we cannot simplify, we write it the same. Well, how to calculate this limit now? Note that x tends to plus infinity, then 6 over x will tend to 0. Also x tends to plus infinity, then 9 over x squared will also tend to 0. The same here, as x tends to plus infinity, 2 over x will tend to 0 and 3 over x squared will tend to 0. What should be the limit then? As you see, what's remaining for us? 5 over 3. Then the limit of f of x at plus infinity is exactly 5 over 3. Well, another example. Here we're going to solve it directly. What should be the limit of f of x at plus infinity? As we have mentioned, we can take the highest degree of x on both numerator and denominator with their coefficients. Then the limit of f of x. Sure, we can apply this method on plus and minus infinity when we need to calculate the limits. Here at minus infinity, the limit of f of x is exactly equal to limit at minus infinity 4 minus 2x squared over 5x cubed. Well, note something, we can simplify x squared with x cubed. Then the limit will be equal to limit at minus infinity 4 minus 2 over 5x. Well, x tends to minus infinity. Then when we divide by x, the limit will tend to 0. So minus 2 over 5x will tend to 0. Another example. As you see here, we have f of x, which is equal to 5x squared plus 6x plus 9 over 3x squared plus 2x minus 3. Well, we have learned how to calculate the limits of such functions at plus infinity and minus infinity. Now what about 0? Note that when x is 0, then 5x squared is 0, plus 6x also is 0. Here 3x squared is 0 and plus 2x is 0. Then we can say that limit for f of x is plus 9 over minus 3, so it's equal to minus 3. Well, another example. Here we have f of x is equal to 6x cubed minus 2x over 3x squared plus 5x. Note something. If we calculate the limit of f of x as x tends to 0, here we have 0 minus 0, which is 0. Also 0 plus 0, it will be 0. Well, 0 over 0 is an indeterminate form. Now how to calculate the limit of f of x in such case? If you know something, we can factorize on both numerator and denominator, we can take x as a common factor. Then the limit of f of x at 0 is equal to the limit at 0 for x into 6x squared. What remains for us on the first term? We have taken x as common. Then what remained from 6x cubed? We are still having 6x squared. Minus, we copy it. We have taken x as common. What remained for us? 2. So it's x into 6x squared minus 2. Similarly, on the denominator, we can take x as a common factor. Then what remains for us? 3x squared. When we pick up x, what remained? 3x. Plus, we copy it. 5x, we have taken x as common. What remained for us? 5. Now, as you see, we can simplify x by x. Well, then limit as x tends to 0 for 6x squared minus 2 over 3x plus 5. Note that here it will be 0 minus 2 over 0 plus 5. We just replace x by 0. Well, 0 doesn't affect on minus and plus, then it's equal minus 2 over 5. So the indeterminate limits that we have learned about are infinity over infinity and 0 over 0. Let's explore some more examples. If we have, for example, the function f of x, which is equal to sine x over x. How to calculate the limit of f of x as x tends to plus infinity? Well, if you note something, we have minus 1 is less than or equal sine x less than or equal 1. Then if we divide all by x, we can get minus 1 over x is less than or equal sine x over x less than or equal 1 over x. In this case, we can say that limit as x tends to plus infinity for minus 1 over x is less than or equal limit as x tends to plus infinity for sine x over x and less than or equal limit as x tends to plus infinity for 1 over x. But if you note something, as x tends to plus infinity, minus 1 over x will tend to 0. Also, as x tends to plus infinity, 1 over x will tend to 0. Then we can say that 0 is less than or equal limit as x tends to plus infinity for sine x over x less than or equal 0. Well, in this case, we can directly say that limit at plus infinity for sine x over x is equal to 0 since it's between 0 and 0. Well, here also we have a rule. If a function f of x is between two functions h of x and g of x, if we have limit at plus infinity for h of x is equal to limit for g of x as x tends to plus infinity equal to the limit at, then we can say in this case that the limit of f of x at plus infinity is equal to I. Another example. As you see here, we have f of x equals x minus radical x squared plus 2. Well, from the first while we can see that it's very easy. But here is another form of indeterminate limits. Why? If we think about the limit of f of x as x tends to plus infinity, note that as x tends to plus infinity, we have x squared plus 2 will tend to plus infinity. Then radical x squared plus 2 will tend to plus infinity. But we have minus here, minus times plus minus. So minus radical x squared plus 2 will tend to minus infinity. But here we are having x which tends to plus infinity. Now plus infinity minus infinity is an indeterminate form. Well, how to calculate the limit in this case? Actually, if we multiply by the conjugate of x minus radical x squared plus 2, what's the conjugate of this form? We replace minus by plus. If we have a plus, we replace it by minus. If we have minus, we replace it by plus. Well, sure, we should multiply and divide by this conjugate. So it's times x plus radical x squared plus 2 over x plus radical x squared plus 2. Note that here we have it as a fraction over 1. Now we can multiply numerator by numerator and denominator by denominator. On the numerator, we can have it in the form of a minus b into a plus b, as if it's remarkable identity a squared minus b squared. So it's x squared minus radical x squared plus 2 all squared over 1 times x plus radical x squared plus 2. When we multiply by 1, it remains the same. Now note that square cancels the radical. Then we will have x squared plus 2, but sure between parentheses since we have minus outside. Well, now we multiply all by minus. Then f of x is equal to x square minus x square minus 2. Note that over sure x plus radical x square plus 2. Note that x square minus x square is cancelled. So f of x is equal minus 2 over x plus radical x squared plus 2. Well, in this case, can we calculate the limit of f of x at plus infinity? Let's see it together. Note that the limit in this case is equal to limit at plus infinity for minus 2 over x plus radical x squared plus 2. Well, when x tends to plus infinity, then x plus radical x squared plus 2 will tend to plus infinity. In this case, the limit of f of x is minus 2 over plus infinity, then it's equal to 0. Another example. Here finally is a special case which is very important. If we have f of x equal x times sine 1 over x. Now how to calculate the limit of f of x as x tends to plus infinity? Here is another indeterminate form which is plus infinity times 0. Why is it plus infinity times 0? Here when x tends to plus infinity, 1 over x will tend to 0 and sine 0 is 0. But we have outside here it's multiplied by x which tends to plus infinity. Then the limit of f of x in this case is plus infinity times 0. It's an indeterminate form. Now how to calculate the limit of f of x? If you note something here, x is x over 1. If we move it to the denominator, we can reverse it to 1 over x. Then f of x is equal to sine 1 over x all divided by 1 over x. Well, how to calculate the limit of f of x at plus infinity in this case? If we take a variable t, which is equal to 1 over x, we can replace 1 over x by t. Note that as x tends to plus infinity, then 1 over x will tend to 0. So we can say that t tends to 0. Then the limit of f of x at plus infinity, sure we can replace here 1 over x by t. So the function is sine t over t. Now as x tends to plus infinity, the limit of f of x is equal to the limit as t tends to 0 for sine t over t, which is equal to 1. Well, why limit as t tends to 0 for sine t over t is equal to 1? There's something which is very important. Let's see it together. Actually, in a trigonometric circle, if we have an angle theta, which is approximately, as you see, equal to 0. Well, if you note something, theta is a central angle. Its measure sure is equal to the arc AB, which is facing it. Well, also if you note something, if we join the chord AB, in this case, isn't it approximately equal to the length of the arc AB? Well, what's the length of the arc AB? If we remember, the perimeter of a circle is 2 pi r. The circle represents for us 360 degrees. 360 degrees give us 2 pi r, but the radius of a trigonometric circle is 1, so 2 pi times 1 is 2 pi. Now the angle theta, which is here approximately 0. What length of the arc AB should it give us? Note that here we can say that the length of the arc AB is in this case theta times 2 pi all divided by 360 degrees. But note that 2 pi is approximately equal to 360 degrees, so we can simplify them. Then the length of the arc AB is approximately equal to the angle theta. Well, now if you note something here, the sine of the angle theta, if we project here from B to get this sine, it's approximately equal to the length of the chord AB, which is approximately also equal to the length of the arc AB, which is approximately also equal to theta. So we can say that in this case, when theta approaches 0, then sine theta is approximately equal to theta. Now what about the limit as theta tends to 0 for sine theta over theta? Since sine theta is approximately equal to theta, then we can say that this limit is equal to the limit as theta tends to 0 for theta over theta. We can simplify here theta by theta, it gives us 1. So it's equal to the limit as theta tends to 0 for 1, then it's equal to 1. Now here we can conclude the rule, which is limit as x tends to 0 for sine x over x is equal to 1. Now, thank you for watching. If you enjoyed this video, please like, share, and subscribe for the continuity of our channel to support you by more and more information with a great appreciation for your support. Thank you all.